Good everyone, my name is Graphics. Now if you look at the front of the screen, you realize we have a bar. But this bar is different from the other bars that we've been solving. This bar area is varying, it is not equal. They have different cross-sectional area. And we are told to find the stress in the three parts and the total elongation of the bar for an axial pull of what? 40 kilonewton. So this is bar of varying cross-sectional area. What we've been doing earlier have been bar of what? Uniform cross-sectional area. So let's see how this works. Now the first thing, if you look at the parameters, we have three different bar. Let me name this A, name this B, name this C, and name this D, right? So if I'm to calculate, we say we should look for the stress in each bar, right? Now calculating for stress. Calculating for stress. Right, these are symbol for stress. We know very well that for section AB, where the section of AB, we're talking about here to here. We know that the stress, right, of section AB is equals to what? The force over what? The area, right? Now this is, let me call it my equation 1. So if you look at this, the force is uniform. We say the force P is equals to what? 40 kilonewton. Now the length of that AB, L, is giving us what? 200 millimeter. That is the length at that point there. Now still the area, we know the area of that AB is giving us what? Pi d square over what? Over 4. Now the diameter given is giving us what? If you look at this, diameter is giving us 50 millimeter. So if I use the 50 millimeter here, so I'm going to be having this to be equals to 22 over 7 multiplied by 50 square, everything divided by what? By 4. Because the pi is 20 over 7, the d is 50, and over what? Over 4. So in putting this into your calculator, we are going to be having the area at that section AB to be 1964.29 millimeter square. That is the area for AB, right? So the next thing we'll do, we've gotten the area, then we put our parameters into equation 1. So in putting the parameter into equation 1, we'll now say that the stress at AB, that is therefore the stress will now be equal to the force, which is giving us 40,000. The force giving us 40,000 Newton, because it is giving us 40 kilonewton. The kilo means 1,000. So all divided by the area, which is giving us 1964.29. So if you do this, the stress will be equals to 20.364 Newton per millimeter square, because force is in Newton and the area is in what? Millimeter square. So this is the stress at section AB. At this section, the stress developed by the bar is giving us what? 20.364 Newton per millimeter square. Now, if I want to calculate the elongation, because we are told, if you look at the top right corner of your bar of your screen, the Young modulus E, let me add it to the parameters. The Young modulus E is giving us 1, that is 2.1 times 10 raised power what? 5 Newton per millimeter square. So if you input it, so we want to calculate for what? For the total, the change of bar AB. So the change means calculating for elongation, right? Elongation, we know we are dealing with what? Section AB, don't forget that. So the elongation, from our formula, we say that the Young modulus, right, is equals to, so we can easily say, or let's ignore this, let's say the elongation delta L is equals to what? The force times the length all over what? The area times the Young modulus. Let me call this my equation 2. So if I input all my parameters into this equation here, I am going to be having the force, which is 40,000, times the length, which is giving us 200, all divided by the area, which is giving us 1964.29, multiplied by the Young modulus E, which is giving us 2.1 times 10 raised power 5. Now, if I move this further, I'm going to be having 40,000 divided times 200 will be, that is 8 million. So we say that 8 times 10 raised power what? 6. That is what we have here. All divided by 19. If I multiply all this, I'm going to be having, that is, if I say 1964.29 multiplied by 2.1 times 10 raised power what? 5, right? So we'll now say that this is going to give us 0.0194 millimeter. So that is the elongation at section AB, right? So we'll move forward. Now we've gotten the elongation for section AB, I've gotten the stress for section AB. So the next thing we'll do, we'll go to what? Section BC. So calculating for stress at section BC, so put it this way, calculating for stress right? So this is what? Section BC. Now write out the parameters. We know very well that the force is consistent, is constant, which is given as 40 kilonewton, right? And that is equals to 40,000 Newton. Now the length is giving us 250. You'll be wondering, where am I getting this parameter from? Now watch. At this point, we're talking about this bar here. We're talking about this bar here. We have the section here. It's giving us 250, that is the length. Then the diameter is giving us 35 millimeter. So let's put the diameter. It's giving us 35 millimeter. So let's see how that goes. So diameter is giving us 35 millimeter. D giving us 35 millimeter, right? Then the next thing that we'll be having should be the Young modulus, which we know it is constant throughout the bar. So the Young modulus E is giving us what? 2.1 times 10 raised to power what? 5 Newton per millimeter square. So what we're calculating for should be the area. So if we're calculating for the area, I'm going to be having this. So we'll now say that the area will giving us what? We say it is pi d square all over what? 4, which is giving us 22/7 multiplied by the diameter, which is 35 square all over 4. So if I input this, my area here will be giving us 962.5 millimeter square. This is the area, right? Now we've gotten the area, so the stress will now be giving us, calculating for our stress. The stress here from equation 1 is giving us what? The force over what? Area. So from here, what is the force given? The force is 40,000 all over the area, which is 962.5, and this will give us 41.56 Newton per millimeter square. This is the stress. Now the next we calculate is for what? To calculate the elongation along section BC. So the elongation for the BC, along BC, is giving us what? Still the force times the length all over the area times the Young modulus. So if we input our parameter here equals to, so we're going to be having the force, which is giving us 40,000 multiplied by what? The length, we know it is 250, all divided by the area, which is giving us 41, which is giving us 962 that is 962.5 multiplied by the Young modulus, which is 2.1 times 10 raised to power what? 10 raised to power 5. So when you input your values, and you're going to have your elongation to be here, we'll have 10 times 10 raised to power what? 6, that's 10 million, all over 962.5 times 2.1 times 10 to the power of what? 5. So if you do this, your elongation will be giving us, so we'll have 0.0495. This will be 0.0495 millimeter. That is the elongation for section BC. Now we want to do that of section CD. So calculating stress for section CD. Now this is section what? Section CD. So we have to write our parameter. We know very well that the force is still 40 kilonewton. We say the force is giving us what? 40 kilonewton, right? Which is giving us 40,000 Newton. And we have the length of that section, which is giving us 200 millimeter. And we have the diameter D of that section, is giving us what? 20 millimeter, right? So it's giving, if you check it very well, it's giving us what? 20 millimeter. Now we also have what is called the Young modulus E of that section of the bar is 2.1 times 10 raised to the power what 5 Newton per millimeter square. And the area, we know the area is given by pi d square over 4, and we know our pi is 22 over 7 multiplied by the diameter d, which is given as what 20 square all over what 4. So if you put your value here, the area will now be 314.29 millimeter square. That is the area. So from here we can now say that the stress, calculating for the stress will now give me force over what over area, and the force we had is 40,000 all over the area, which is 314.29. So this will now give us 127.27 Newton per millimeter square. Now this is the stress for section CD. Now the Young modulus, I mean the elongation. So calculating for the elongation, calculating for elongation for what? For CD. Now the elongation, we know that delta L is given force times length all over the area times the Young modulus. Now what is the force? We know it is 40,000 multiplied by the length, we know it is 200 all over what? The area, which is 3.14, that is 314.29, right? Then we have the Young modulus, which is times 2.1 times 10 raised to the power what 5. That is the Young modulus. So if I input my value here, I am going to have this to be 40,000 times 200. That will give us 8 million, which is 8 times 10 raised to the power what 6, all divided by 3.14, no 31, not 3.314.29 times 2.1 times 10 raised to the power what 5. So if I do that, I'm going to be having, we have our value to be equal to what? 0.1212 millimeter. Now we've gotten the total elongation. So now calculating for what the question says, look at the top right corner of the screen. It says that what we should look for the total elongation of the bar for axial pull of 40 kilonewton. So calculating for total elongation from A to what? To D. That means we want to look for the total elongation from A down to D, all the lengths, right? So we know that the total elongation delta L will be giving us what? Elongation along AB plus the elongation at what? BC plus the elongation at CD, right? So if I input my parameters, my value here, we're going to be having this. Elongation at AB calculated at the beginning is giving us what? 0. Look at this elongation at section where section AB is giving us 0.0194. So we have 0.0194 plus the elongation at BC, which is what we calculated here. Elongation at BC is giving us 0.0495. 0.0495. So let's do that. 0.0495 plus elongation at CD, which is what we have here, and that's giving us 0.12 1, 2. So if I add everything all together, I am going to be having this. So the total elongation will be giving us 0.190 millimeter. So the total elongation along the bar is giving us what? 0.19 millimeter. So if you found this video helpful, please don't forget to click on the subscribe button. Thanks for watching.